subject I want to discuss is model selection. So model selection is the following problem. So you have some data and you want to describe this data. Let's say this is a sequence of independent observation of a certain system. Now you want to find what is the model that describes this data. And so if you have a particular model, then you can estimate the parameters, as we just said. But imagine the situation where you have many models that depend on different parameters. And essentially you have to decide which of these best describe your data. Okay. So one idea is okay. So I take this data, I compute the likelihood of all this model, and I take the most likely model, the model which has the highest, the maximum likelihood among all these models. So this is not a very good idea. Okay, let me show you why this is not good by a classical example. Well, essentially, imagine that your point, your data is actually each point xi is actually a pair of points. Let's call it say zi and yi. Okay. So if you plot your points in on a plane, then you may get some particular shape. Okay. And now your model. So your model, well, the simplest model you can think of is to say, well, okay, y does not depend on z. So essentially, your model is that the data, all the values of y are essentially the same, but then there is an error. There are say some fluctuations. So these points y are just randomly distributed around a certain average, which is this. You can have a little bit better model to say, well, no, actually, the points which are here are a little bit higher than the points which are here. So maybe a better model would be just a straight line, the average of y, the expected value of y increases linearly with z, and then there are points are distributed around this average. And you can say, well, okay, but this maybe is not the full truth, because when these points bend a little bit down, so maybe this is a better model where I also assume that there is a certain curvature. Okay. And you can go on like this, and say, for example, in the end, you can take a model where essentially your f of x given theta is essentially something like maybe a Gaussian with some variance of e to the minus say y minus f of z squared divided by 2 sigma squared. So this would be a model that tells you that there is a function f, and then your the values of y is just a Gaussian variable around a mean, which is f of z. And then you can take that f of z is so just a constant A0, or this would be the model 1 is of a straight line, and f of 2 z is A0 plus A1 times z, and you can go on like this. And in the end, you can get a model, say Fm, where essentially you have a polynomial of degree m, and the more terms in this polynomial you take, the better you will be able to estimate this function here. And in particular, if you take, say, n, your number of terms in this polynomial to be equal to the number of points in your sample, then you can get a curve that goes exactly through all these points. Okay, so so because essentially this is essentially you have n-ordered polynomial, and you have to essentially solve an equation. So essentially you can solve this problem. And when you do this, you find that your best model would have actually sigma equal to 0. So the error with which you describe the points is essentially equal to 0. But so what is the problem with this model here? So the problem is that if you get a new point, then a new point, let's say here, then it is very unlikely that this new point will be described by your model. Generally, this new point will be very far from the prediction of the model for this new point. So this is the issue of generalization. So a very complex model is very good at describing the data, but is very bad at describing data that are not yet seen, that you have not yet seen. So for example, if you take a simpler model like the straight line, the error in this of a new point will be more or less of the same order of the error of the points that you have already fitted in the sample. Okay, and this is more or less what you would like. You would like that your model does not only fit well the data, but it also generalizes and it describes data that you have not yet seen. Okay, so this means that when you want to choose between these different models, you don't have only to take into account the likelihood, because the likelihood takes into account how well you describe the data, but you have to take into account something else, and this something else is the complexity of the model. You have to penalize the likelihood of the model by a term which is called complexity, that we call generally complexity, and this term will be very high if you have a very complex model, so that in the end you will choose a model in between that establish a trade-off between say accuracy, describing well the data that you have, and complexity. Okay, so how do you do this in practice? So there are different recipes for doing model selection, And I want you to get an idea of what is the idea that is behind each of this idea. Okay. So the first one is what is called archaic. Information criterion. Information criterion. Or it's called AIC. Okay, and Archaic was a statistician, Japanese statistician, remarkable one, and he came up with this idea in his paper, and his idea is the following. So imagine that we have, say, the space of distributions. Okay. Now, in the space of distribution, you can think at each of these models as being a different manifold. Okay, a different curve. Okay, so this is one model. This will be another model. Okay. And now, say you have, let me draw also another model. Okay, so now you have, say, your data, which is somewhere here, your true model. Okay, so let's say that this is your true model, which is none of these model actually describes is the true model. This is a general fact of life. It was a very say famous statement by a statistician saying that every model is wrong, but some models are useful. So every model is wrong, but yet here you would like to find what is the, you would like to score these different models according to how far they are from the true model. Okay, so imagine that now let's consider this yellow model here, and so this, so the best model that describes the true model would correspond to a certain theta hat. Okay. So now your what you want is really to minimize to rank these models according to their distance to the true distribution. Okay, so for each of these, you would like to compute something like the DKL between your true model and the model that among these is closest to the truth. Okay, then you would like to find the minimum of these guys. Now, what is the problem in here? Well, the problem is that you don't know what the true model is, and you don't know neither what this theta hat here is. So what you have is actually a sample. What you have is a sample and a type, and when you do your estimation, so what you can estimate is actually a maximum likelihood, the maximum likelihood parameters. Okay, So the idea is that you would like to get an estimate of the true distance in terms of the distance that you can measure, which is essentially the DKL between your sample and the maximum likelihood probability distribution. Okay, so how can we do this? Well, the idea of is sort of a little bit complex, but I'll try to explain. So first of all, you write DKL distances as cross entropies. So if I define this T minus S of T and theta hat, where essentially let me define say S of P and Q as generally the integral, the likelihood of the log likelihood of Q with respect to distribution P. Okay, so now very good. So now we don't know this, but what we can argue is that say this S of T given theta hat, this theta hat this theta bar will be close to theta hat. Okay, so I can expand this, say if you want, theta hat, S of T and theta hat, around S of T and theta bar. And now, if I expand around theta bar, then the first term will be the derivative with respect to theta bar of S of T and theta bar times theta hat minus theta bar plus 1/2 the second derivative with respect to theta hat squared of S of T theta bar times the square of this plus higher order term. So first observation is that this is going to be equal to 0 because theta hat is the maximum. So this theta hat is the closest point to T, so it's the one that maximizes this object here. So, and the second thing is that this term must be negative. And if you work out what this second derivative is, well, not surprisingly, you again find our friend, the Fisher information. So the expression for this is that this is given by minus 1/2 times the theta hat minus theta squared times the Fisher information. Okay, so very good. So now I'll write down formulas for one-dimensional case, but actually the way you should think about this is really that we are dealing with, say, a system with models with more than one parameter. Okay, so this is a vector, this is a matrix, and this is a vector. So this is transpose vector, if you want. Okay, so now how can we estimate this? Well, the idea of IKEK is to say, let's say that this can be estimated by saying that the variable theta hat actually is like a Gaussian variable around theta bar, and its covariance is actually given by the Fisher information, by the inverse of the Fisher information. So this is essentially 1/2 times, so if you say that the covariance of the theta hat is 1/n times the Fisher information, then you see what you get here. Here you get 1/2n times the trace of j times j to the minus 1. But this is the identity, and the trace just gives you the number of entries, which is the dimension. This is S of t, theta bar, minus the trace of the identity is just the size of the matrix, which is the number of parameters, d, divided by 2n. Okay, so this is, say, an approximation, and it allows us to say that, well, this distance, I can approximate it as S of t and t minus S of t and theta hat. Now I replace this theta bar by this plus d over 2. Okay, so here I have plus d over 2n plus higher order terms. Okay, so very, very good. So again, we have a problem here that we do not really know what this true distribution is. Okay, so and okay, so how do we do this? So the idea here is essentially the following. So imagine that we consider the DKN between the true distribution and theta hat. Okay, so so this can be written as the cross entropy between the true distribution and itself minus the cross entropy between the true distribution and theta hat. Okay, which is essentially what I want to estimate here. Now so the idea is that here, so what I want to do is to replace this by this formula here. So where this is S of so let me first write and then tell you what I'm doing. Oh no, sorry. So the first step is to substitute this by this formula here, minus S of T and theta hat plus K over D over 2n. I'm again using this approximation here. Let me rewrite it. So this is S of T and theta hat minus T over 2n. Okay, so first I'm doing this. And now the idea is that here I have this distance here. And now what I want to say is that, well, T is very close to my empirical average. So that essentially if I, in this equation here, if I substitute here and here T by P, I'm not going to make a big error, essentially. Because essentially these two distribution, when n is very large, they are going to be very close to each other. Okay, so the idea is that okay, is to say here I'm going to put the empirical. I'm going to estimate this S using the empirical distribution instead of the true distribution. And by the law of large numbers, this is makes sense. And this is what I get. Okay. Now, now the last step is that this point here, I can estimate, like in this equation here, I can estimate that S of Px and theta hat. Now I can expand this expression around theta hat this time. So why theta hat? Because theta hat is the maximum. Theta hat is what maximizes this function as a function of theta. And you can do the same argument as here and figure out that so this should be smaller, this should be smaller than this. And the difference is just minus, again is minus d over 2n, can be estimated to be minus d over 2n. Okay, so then so the end result of this is that you can from this equation you can you can estimate is S of t and theta hat to be the difference between these two, and then plus this term here. Okay, and so this tells you in the end that so if I if you can divide this as S of t and t minus at the place of so if I take these on the other side is S of t and t. Sorry. Here I have this S of t and theta that sorry. Is here S of t and theta, and theta hat from yes from here is going to be S of t and t minus S of px and t plus S of px and theta hat plus d over 2n, and so, and then I'm going to use this expression here. So sorry, there's a minus. Yes. So if I put everything here, S of t and t, which is this, minus this, which is minus S of t and t, plus S of t, and instead of this, I'm going to take this, which is S of so instead of this equation, I should take yeah, so this should be sorry, yes, so I'm so the S of t and theta hat. Okay, so I'm using this equation and I'm using this one. Okay, and then in this equation, so I have S of t and theta hat minus this thing, which is minus this thing, which is S of theta minus plus S of px and t minus here, instead of S of p, x and theta, I'm going to put this. So minus S of px and theta hat plus d over 2n, and then I have plus d over 2n. Okay, so then the final result is this, that this and this go away. So in the end you have that your estimate of the distance between the true distribution and the base parameter of your model is given by S of Ex and T minus S of Ex and theta hat plus d over 2, so d over n. Okay? So you see, now this is very nice, so because, well, this fact, you don't know the true distribution, but this is a constant, okay? It's a constant, and this is the same for all models. You don't care about, so this constant will be the same for all models. Whereas this constant here, this is just the likelihood, or minus the likelihood. And this is a constant that depends on the number of parameters of this particular model, D. And so what this tells you is that in order to compare these different, to find which of these models is the best one, you should just penalize the likelihood, the log likelihood, by a term which is d over n. Okay? Okay, so this is archaic information criterion. So there is another criterion which is is called, instead of AIC, is called BIC. Okay, so instead of AIC, it's called BIC, and instead of archaic, it has the name Bayesian Information. So what is the idea of the Bayesian information criteria? Well, the idea is that if you, what you should do, if you are a Bayesian, you should compute what is the probability of model M given the data, and then you should choose the model which is more likely given the data. So how do you compute this? Well, by Bayes' rule, this is just the probability of the data given the model times prior probability of the model, and then you should just sum over all models the same thing. Now this is just Bayes' theorem. Now if you a priori want to say that all models are equally likely, so this is just a constant, then this constant goes away, and this tells you that finding the most likely model, or the model which is more probable, is finding the model for which the data is most likely. Okay, instead of maximizing this, you can maximize this. Okay, and what is P of x given m? Well, it's just the integral over all the parameters of the probability of the data, and as we said last time, you can write the probability of the data e to the n times the log likelihood of the parameters. Let's say this, the log likelihood of model m given the data times a prior distribution. This is also for model M. Okay. Now the idea is that so if you want to be even more precise, okay, so let's so how do you do this integral when n is very, very large? You do it with the saddle point. We have already done this integral a couple of weeks ago, so a couple of lectures ago. So this is just the square root, well, it's 2 pi divided by n times the determinant of the Jacobian of this matrix. Let me take just exponential, an exponential family. So that we know that the Jacobian of the likelihood is given by the Fisher information. So this is, so what you get is this factor, because when you change the variable in the Gaussian integral, you have d-dimensional Gaussian integral, and so you get this factor here, then you get a factor 1 over the square root of the determinant of J, computed in the maximum likelihood parameters. And then you get e to the n times the log likelihood computed at the maximum. Okay, and then you get the p0 of m computed also at the likelihood. Okay, so this is all there is. And so if you want to compute the log of the log of the probabilities, say, divided by n, what you should have are the log likelihood. This is given by the log likelihood. And then you have the log of this term divided by n. So this gives you plus or minus d over 2n times the log of n over 2 pi times plus minus 1 over n times 1 over 2n times the log, or 1 over n times the log of square root of the determinant of J. Okay. Very good. So essentially you see that the leading term here is a term which is minus d over 2n times log n. So you, according to the Bayesian Information criterion, what you should do is if you want to choose between the different models, you should compute the likelihood at the maximum, and then subtract a term which is minus the number of parameters divided by 2n times log n. Okay? So this only depends on the number of parameters. However, this is only the next to leading term, the leading correction, because there are also other constants that you could consider. Okay, so in some sense, if you compare this, the penalty for the Bayesian Information criterion is d over 2n times log n, is more severe than in the archaic information criterion, where the penalty is just d divided by n. And this and this is because the argument that you make is a different one. So So here, let's say, what we do is Bayesian argument, where we take, say, the expected value over of the likelihood itself. Here instead, if you think about it, we reason about the log likelihood directly. Okay, so this difference is what makes you accounts for this log n. Okay, so there is one last question. There is also a term which is minus 1 over n plus 1 over n times the log of the prior, computed in theta hat. And when you can check that, the interesting thing is that when you use Jeffreys prior, I remind you that Jeffreys prior was a probability distribution which was proportional to the square root of the determinant of J. Then these two terms with Jeffreys prior becomes just minus 1 over n times the log of the integral over all the parameters of the square root of determinant of the Fisher information. And what is important about this is that on the Bayesian, if you take a Bayesian point of view with the Jeffreys prior, which is maximum entropy prior, maximum uninformative prior, then you get that the penalty to leading order does not depend on the data. So this depends on the data through theta hat, but if you take Jeffreys prior here, then these two terms just give you a penalty that does not depend on the data. And it's a characteristic of the model. Okay, it tells you how much this model is complex. Okay, so there is a last bit that I wanted to tell you about, is that essentially you get exactly this same formula with this expression here if you take a perspective which is completely information theoretic, and this perspective is the perspective of minimum description length. So the problem, minimum description length, so you look at Bayesian, you look at a problem of model selection as a problem of coding. Okay, so what you want to do is your different models in a coding perspective are different ways in which you can compress your data in the most efficient way. And essentially what you would like is to find a model that is able to compress your data as much as possible. So if you look at this problem from this perspective, you have the usual coding perspective of Alice and Bob. And so Alice has this data X, and he has to send it to Bob. And Bob knows that this data was generated from some distribution f of x in theta, but does not know what parameters theta, what are the parameters theta. Actually, you can think that this is being like the typical experimental setting where this guy is the experimentalist, is doing the experiment, is getting the data, and then this guy is a theorist, so from the data he wants to estimate what are the parameters of the theory. So this experiment is done precisely because you want to know the parameters theta. But when Alice before the experiment is done, Bob wants to know how much disk space he has to allocate on his hard drive. And so this is a very well-defined problem. And if you solve this problem, you find out that the number of bits per character that should be allocated is precisely equal to this. It's precisely equal to the number of bits that are needed to describe one data point at the maximum likelihood parameters, plus this penalty minus this penalty, sorry, so the number of bits should be minus this, okay, with a minus sign. There should be a minus sign here. So this becomes an overhead of a number of bits that are needed, and this has the usual behavior of being, say, 1/2 log n for each parameter, because you are reducing the entropy of parameter by a factor of 1 over square root n. And then there is this term, and this term is actually a term that, if you want, this term would describe how many bits you need to describe independently each of the parameters. And this term tells you how much, instead, these parameters depend on each other. So this tells you, this comes about because these parameters are not independent random variables. And so this term here is an intrinsic complexity of the model, and it's called parametric complexity. And it essentially it's a measure of how complex a particular model is. Okay.